In our last video, we talked about ionic bonds, which are formed by the transfer of electrons from one atom to another. In this video, I want to talk about covalent bonds. So, some atoms do not transfer electrons from one to another to form ions. Instead, they form a chemical bond between the two atoms by sharing a pair of electrons. This is what is known as a covalent bond, or the sharing of a pair of electrons between two atoms. And most of the time, each atom contributes one electron to that pair. In our video on ionic bonding, we said that elements on the left side of the periodic table tend to donate electrons to elements on the right side of the periodic table. And this is made possible by the difference in electronegativities between those elements. So electronegativity is the ability of an atom to attract an electron. Electronegativity increases as we go from left to right through a period in the periodic table. So those atoms on the left are low in electronegativity, so they're willing to give up an electron, while the atoms on the right side are high in electronegativity, so they are willing to accept an electron. So let's have a look at our second row elements, and these are all the elements that make up the second row of the periodic table, and carbon is contained in that row. Now, I said that electronegativity increases as you go from left to right across the periodic table. So atoms to the left of carbon are less electronegative than carbon, tend to give up electrons. Atoms to the right of carbon tend to be more electronegative than carbons, and they tend to accept electrons. Carbon, look at carbon, it's right here in the middle. It has an intermediate electronegativity. So because of that, carbon neither gives up nor accepts electrons, but rather it shares electrons with other elements. And in reality, all of these elements from beryllium to fluorine are capable of forming covalent bonds. Lithium pretty much only forms ionic bonds. Beryllium can form both. Fluorine can also form both. So as I said, electronegativity is the measure of a tendency of an atom to attract electrons. And when two atoms that share a pair of electrons, or two atoms that share a covalent bond, have differences in electronegativity, then they're not sharing those electrons equally. The more electronegative atom is going to pull harder on that pair of electrons. It's going to be kind of greedy and wants all of the electrons for itself. So we say that those kinds of bonds where you have a difference in electronegativity are polar covalent bonds. So the polarity of a bond is determined by the difference in electronegativity between the two atoms that make up that bond. If the electronegativities are the same, they're sharing those electrons equally and that bond is nonpolar. But if the electronegativities are very different, then that bond is going to be very polar. They're not sharing the electrons equally. So how would you know if a pair of atoms is going to form a covalent bond, or an ionic bond, or a polar covalent bond? So you look at the difference in the electronegativities. If the difference is less than about 0.5, we say the bond is covalent, so their electronegativities are close to each other. If it's greater than 1.9, we say that the bond is ionic. And anything in between those numbers is going to be considered a polar covalent bond. And these numbers aren't written in stone. This is just a general rule of thumb. So let's just look at a few examples. For instance, if I were to take two hydrogen atoms, each hydrogen atom has one electron, and I use those two electrons to form a bond between them, or they're sharing electrons. Now, because each of those hydrogen atoms is sharing electrons, they each have two electrons in their valence shell. But since we have two hydrogen atoms here, they are equal in electronegativity, so that bond is going to be nonpolar. So that's a nonpolar covalent bond. If I take two fluorine atoms, remember that fluorine is in group 7 of the periodic table, so 7 electrons in the valence shell. I can use one electron from each of the fluorines to make a bond between those two fluorines. But again, because it's two fluorines, their electronegativities are identical, that bond is going to be nonpolar. So these are two nonpolar covalent bonds. On the other hand, if I take a hydrogen atom and a chlorine atom, hydrogen has one electron in its valence shell, chlorine has 8. If I use these electrons, one from each atom, to make a bond, now chlorine, because hydrogen donated or hydrogen is sharing an electron with the chlorine has 2 electrons in its valence shell. It can pretend it's like a noble gas. Hydrogen has 2. Did I say 2 for chlorine? I meant 8 for chlorine and 2 for hydrogen. Now, these two elements are from opposite ends of the periodic table, and while this bond is actually covalent, it is polar covalent. The bonded atoms are different, and they have pretty big differences in electronegativities. So let's look at the electronegativities of some of the elements in the periodic table. And as I said, electronegativity increases as you go from left to right. So starting here at lithium, we're at 1, all the way to fluorine, which is 4. And it also increases as you go from the bottom to the top, starting here from iodine at 2.5 up to fluorine at 4. So the element at the upper right corner of the periodic table should be the most electronegative element, aside from the noble gases, that is, and that element in the upper right corner would be fluorine, and fluorine is indeed the most electronegative element that we know. Now let's look at some of the differences for ionic, covalent, and polar covalent bonds. The differences in electronegativities, I mean. If we look at potassium fluoride, potassium has an electronegativity of 0.8, fluorine an electronegativity of 4, so we have a difference of 3.2. So that's definitely going to be an ionic bond. Let's look at the carbon-hydrogen bond. Carbon has an electronegativity of 2.5, hydrogen 2.1, so we have a difference of 0.4, and that's less than that cutoff of 0.5, right, for a polar covalent bond. So this one is nonpolar. Carbon-hydrogen bond is nonpolar. Obviously, a bond between two of the same elements is going to be nonpolar. But let's look at OH. Oxygen 3.5, hydrogen 3.1, hydrogen 2.1, right? So we have a pretty good difference, about 1.4, between the oxygen and the hydrogen, so that's going to be a polar covalent bond. So in this table, I'm showing you the dipole moments of different kinds of bonds between different atoms here. So it's a measure of the polarity of a bond. So if we look at a carbon-carbon bond, the dipole moment is 0 because carbon and carbon have equal electronegativity, so this is not a polar bond. But if we look at a hydrogen and a fluorine, they're from opposite ends of the periodic table, right? So going to have a big difference in electronegativities, so the dipole moment is also going to be large. So in this table, the HF bond is the most polar among this list. So I just put this up here just so you can get an idea of what bonds are polar and what bonds are not polar, and where their dipole moments would be. So carbon and the halogens, because generally the halogens are pretty polar, they're all going to be polar covalent. Carbon oxygen, carbon nitrogen is a little bit polar, but not terribly polar. So in general, the farther apart two elements are from each other on the periodic table, the bigger their difference in electronegativities will be, and the larger will be their dipole moments for the bonds between those two atoms. So I want to show you a couple of different ways that we represent a polar covalent bond. And what we do is we label the most electronegative element, the more electronegative element, with a partial minus, right? So this is a partial minus charge on the chlorine, because chlorine is more electronegative than hydrogen. And we label the less electronegative element with a partial positive, or a delta plus, in other words. So we have HCl, right? So here I'm showing this bonding pair of electrons as a line, and when we talk about representation of structure, you'll see that that's just kind of a shorthand notation, that this line is meant to represent that shared pair of electrons between those two elements. These dots represent the non-bonding electrons. So we have a few molecules here. We have water, which has OH bonds. Oxygen is more electronegative than hydrogen, so that's going to get the partial negative. The hydrogens get the partial plus. So we also have ammonia, which has NH bonds, right? Nitrogen is going to be, it's farther right in the periodic table than hydrogen. It's going to be more electronegative, so we label that with the partial minus, and the hydrogens with the partial plus. Another way that we do this is we draw an arrow pointing towards the more electronegative element and put a little cross at the end next to the more electropositive element, and that little cross is supposed to represent a partial positive charge. So that's just a couple of different ways that we represent those polar covalent bonds. So it's really important to understand the nature of a bond between two atoms when we're talking about organic chemistry and organic reactions, because this really influences in a very significant way the reactivities of these molecules. Another way that we represent electronic distribution is through these electrostatic potential maps. So the red is supposed to represent more negative areas, where the blue is supposed to represent more positive areas. Yellow and green and orange are sort of in between. So if we look at a molecule, a diatomic molecule like H2, we have two hydrogens. They are equal in electronegativity, right? Each hydrogen. So that's going to be nonpolar, right? So we don't have either red or blue in this molecule. But if I look at lithium hydride, lithium is not electronegative at all. Hydrogen's not very electronegative, but it's more electronegative than lithium. So the red represents the hydrogen, right? The region of high electron density, and the blue represents the lithium. And again, for HF, fluorine, the most electronegative atom that we know, that's going to be red. Its hydrogen is less electronegative than fluorine, so that is going to be blue.